Close your eyes for a moment. Stay with me. Because what we're about to explore isn't something you can drift through. What if the ground under your feet isn't really ground? What if the stars you've looked at your whole life as those distant burning suns are just part of a constructed background? What if your memories, your childhood, every conversation you've ever had, every ordinary day, were all created at once the moment something started running? This might sound like science fiction, but it isn't. These are real questions taken seriously by some of the most careful thinkers working today, and not because they want them to be true, but because the logic keeps leading back to the same unsettling possibility, that reality might not be what we think it is. Tonight we're going to take our time with that idea, not to convince you, not to alarm you, but to follow the argument as far as it goes, because by the end of this journey, you may not have a final answer, but you will see the world differently, quietly, permanently. Let's begin. Here's the thing about the simulation hypothesis. It doesn't sneak up on you from the fringe. It doesn't arrive in the mail wearing tinfoil and conspiracy theory. It walks in through the front door of physics, philosophy and mathematics, and it sits down at the table like it belongs there, because it might. The idea that reality could be a constructed system, a digital environment generated and maintained by some external intelligence or technology, is not a new one. Humans have been brushing up against this feeling for thousands of years. The ancient Greeks spoke of Plato's cave, where prisoners chained underground could only see shadows on a wall and mistook them for reality. Hindu philosophy described Maya, the great cosmic illusion that veils true existence. Buddhist traditions spoke of the constructed, impermanent nature of all perception. Even Descartes, sitting alone in his study in 1641, ran the thought experiment with rigorous honesty. What if an evil demon is deceiving me about everything? What if my body, the world, even mathematics itself is a fabrication designed to mislead? His answer was famously elegant. I think, therefore I am. He reasoned that even if everything else could be faked, the very act of thinking proved that something, some consciousness, was genuinely present. But Descartes didn't have the conceptual vocabulary we have now. He didn't know that thinking could be modelled in code. He didn't know that something resembling awareness could emerge from the right arrangement of information. He didn't know that I think therefore I am might simply mean the program is currently running. That's the uncomfortable update to his 400-year-old insight, and that update is exactly where our investigation begins. So let's ask the question plainly. Could the entire universe, not just our planet, not just our galaxy, not just the observable cosmos but all of it, be a simulation? Could the laws of physics be code? Could the constants that govern the behaviour of matter and energy be parameters set by a designer, rather than features of a brute, uncreated reality? And here's the thing that makes this more than philosophy. The case for it is actually quite strong. Not proven, not settled, but strong enough that serious physicists, serious mathematicians and serious philosophers have looked at it without flinching and come away saying, we cannot rule this out. We genuinely cannot. And that's where it gets interesting. There are 4 questions we're going to follow all the way through this investigation. First, is there a logical reason to think we might be simulated? Second, does the physical universe itself show signs of being a constructed system? Third, what would it mean for consciousness, identity and meaning if we were? And fourth, what do the most recent arguments against the hypothesis actually say, and are they convincing? Hold those 4 threads. We'll pull on each of them one by one and see what they reveal. In 2003, a philosopher at Oxford University named Nick Bostrom published a paper with a modest title and an immodest conclusion. The paper was called, "Are You Living in a Computer Simulation?" And it didn't argue that we were simulated. It did something more precise and in some ways more unsettling. It built a logical structure, a trilemma, from which there is no clean escape. 3 propositions. One of them must be true. There's no fourth door. Here's how Bostrom constructed it. He started with a simple observation. At some point in the future, if technological civilization continues to develop, it will likely become possible to create detailed computational simulations of entire societies, including simulated minds that experience those simulated environments as real. This isn't science fiction anymore. We already live in a world where video games simulate physics, where AI systems generate realistic conversation, where digital environments fool the senses in increasingly convincing ways. The trajectory is clear. Scale that up by centuries, by millennia, by whatever gap separates us from a truly post-human civilization, and the capacity for what Bostrom calls ancestor simulations, detailed recreations of the past, becomes plausible, not certain. Plausible. And plausible is enough for the logic to bite. Now here are his 3 propositions. Either almost all civilizations at our level of development go extinct before reaching that technological maturity, meaning the graveyard of the cosmos is full of species that never made it far enough to run a single simulation. Or virtually every civilization that does reach that maturity decides, for whatever reason, never to run ancestor simulations. Perhaps they find it unethical. Perhaps they lose interest in their past. Perhaps they develop in directions we can't predict. Or we are almost certainly living in one of those simulations right now. The mathematics behind the third option are what give it such gravitational pull. If even one technologically mature civilization ran just a handful of high-fidelity simulations of its own past, the number of simulated minds would rapidly outnumber the minds in base reality. Run thousands of simulations. Let each of those simulate their own descendants, who run more simulations. The numbers become astronomical. The ratio of simulated conscious beings to non-simulated conscious beings tilts overwhelmingly toward the former. And if you are a conscious observer, and you are because you're experiencing this right now, probability says you are more likely to be one of the many than one of the few. What makes this a trap rather than just an argument is that none of the 3 exits are comfortable. The first option, civilizations don't make it, implies something deeply troubling about the future. It implies some kind of great filter ahead of us, some catastrophic barrier that technological societies consistently fail to cross. Nuclear annihilation, runaway artificial intelligence, ecological collapse. Something in the architecture of advanced civilizations tends to terminate them before they ever build a godlike simulation capability. If that's true, the universe is quieter and more tragic than we'd like to believe. The second option, they make it but don't simulate, requires you to believe something oddly uniform about the psychology of every advanced civilization that has ever existed or will ever exist across the entire cosmos. Every single one, without exception, collectively decides we will not recreate our past. We won't do it for science, we won't do it for entertainment, we won't do it out of curiosity or nostalgia or philosophical inquiry. Not one of them. In every galaxy, in every epoch, across billions of years of civilizational development, not one flicker of interest in looking backward. Does that seem like a realistic picture of curiosity-driven intelligence? It strains credibility. And the third option, we're in the simulation, while extraordinary, is actually the most probabilistically consistent, given that the first 2 options seem unlikely. Not impossible, unlikely. And Bostrom's point is not that option 3 is correct. His point is that we cannot casually dismiss it. Here's what Bostrom himself has said when pressed on this. He has estimated roughly a 20% personal probability that we're in a simulation. 20% is not certainty. 20% is also not a rounding error. It's the kind of number that deserves to be taken seriously. The kind of number that should make you pause and look slightly differently at the chair you're sitting in, the room you're in, the sky outside your window. Not with dread, with curiosity. Because the honest answer to the question, are we simulated, is not yes, and it's not no. It's we don't know, and the logic prevents us from being confident we're not. That's a strange place for a species that has mapped the genome and landed on the moon. But it's where we are. Okay, so suppose option 3. Suppose we are, in some meaningful sense, part of a simulation. The natural next question is almost childlike in its simplicity. Why? Why would anyone do this? Why would an advanced civilization invest the computational resources, surely enormous, perhaps unimaginably so, in constructing something as detailed as a universe with 13 billion years of history, hundreds of billions of galaxies, trillions of stars, and on one small planet orbiting one unremarkable star, a species complex enough to ask the very question we're asking right now? What's the payoff? The most intellectually satisfying answer is also the most personal one. We might be an ancestor simulation, not entertainment, not art, not an experiment in suffering, history, archaeology, memory preservation. Imagine a civilization 1,000 years from now, maybe 10,000. They've survived the turbulent adolescence of technological power. They've figured out fusion and then moved beyond it. They've solved aging, spread through the solar system, perhaps beyond it. They are, in every meaningful sense, post-human. They are something we'd barely recognize as descended from us. And yet, like every culture that ever existed, they have historians. They have the impulse to look backward, to understand where they came from, to feel the texture of the past rather than merely read about it. And with their computational power, reading about it isn't the only option. They can recreate it. They can run the 21st century not as a thought experiment, but as a functional model. They simulate cities and seasons and elections and arguments and breakfasts and quiet nights and you. They simulate you, having this experience, thinking these thoughts, wondering about this exact possibility. Because that's what their ancestors did. And you, from inside the simulation, are as real as a historical record can be. More real, perhaps, than a book. You're the living data of someone else's past. What makes this recursive in a way that's genuinely disorienting is the following. If we are in an ancestor simulation, we are presumably modelled after whoever is running it, which means when we eventually reach our own level of technological maturity, if we do, we will also build ancestor simulations. We will create simulated minds who believe they're living in their own 21st century, asking their own versions of this exact question. Simulations inside simulations, layers of constructed reality, each one convinced it's the real one, each one generating the next. How deep does it go? Bostrom's math suggests there's no principled reason it would stop at any particular depth. A single base civilization could give rise to millions of nested realities. The further down you go, the more likely any given conscious observer is to be nested somewhere in the middle of the stack. Not at the bottom, not at the base, but somewhere in the depth of an architecture so vast and layered that the word real starts to lose its reference point. There's an old philosophical quip, turtles all the way down. An elderly woman insists to a scientist that the Earth rests on the back of a giant turtle. And what does the turtle stand on, he asks. Another turtle, she says. And that one? Young man, she replies, it's turtles all the way down. The ancestor simulation hypothesis has something of that quality to it. Simulations generating simulations, each one producing the next, potentially without end. Except that somewhere in Bostrom's framework there presumably is a base reality, a first mover, an original universe in which the first civilization developed without being simulated, and from which the whole recursive cascade was initiated. Or perhaps not. Some versions of the hypothesis allow for something more radical still. A loop. A structure in which the bottom layer creates the top, in which causality doesn't work the way we assume it does outside the confines of our physics. A structure so strange that asking which reality is real would be like asking what lies north of the North Pole. A question that sounds perfectly meaningful and is, in fact, geometrically empty. But let's hold on to the idea of a base reality for now. Let's assume it exists. Let's ask what that changes. And the answer, perhaps surprisingly, is not as much as you'd think. Because if you're simulated, so is everyone you love. Your joy is their joy. Your suffering is their suffering. The simulation isn't playing a trick on just you. It's running for everyone. You're not alone inside this. You are one pattern among billions of patterns, each one as complete and as present as you are. And there's something in that which is, if not comforting, then at least not lonely. Here's something most people don't appreciate about our universe. It is bizarrely, improbably, almost suspiciously well configured for the existence of complex things. The fundamental constants of nature, the numbers that describe the strength of gravity, the behavior of nuclear forces, the rate at which space is expanding, they're not arbitrary. They're precise. Not just precise, but delicately, carefully, almost obsessively tuned to allow for the emergence of stars, of planets, of chemistry, of biology, of minds. Change any of them by even the tiniest fraction, and the universe collapses into sterile simplicity, or expands too fast for anything to form, or burns through itself in microseconds. What we have instead is a universe that works, and that working is more improbable than it has any business being. Take the gravitational constant, the force that holds matter together at cosmic scales, that makes planets orbit stars and stars orbit galaxies. If that constant were even slightly larger, not dramatically, just fractionally, stars would burn through their fuel far too quickly. They'd ignite, blaze brilliantly, and die before the complex, slow chemistry of life had any chance to emerge. Slightly smaller, and stars never ignite at all. The universe stays dark and cold, hydrogen gas drifting endlessly through empty space, never condensing, never fusing, never making carbon or oxygen or iron. The window in which life becomes possible in terms of this single constant is extraordinarily narrow. A few percent in either direction and we don't exist. Then consider the strong nuclear force, the force that binds atomic nuclei together. Too strong and hydrogen atoms fuse too readily. The universe becomes a sea of helium with no water, no organic molecules, no chemistry that could generate anything interesting. Too weak, and nuclei fall apart before they form. No atoms heavier than hydrogen, no periodic table, no complexity of any kind. The margin for life, in terms of this constant alone, is almost vanishingly slim. And then there is the cosmological constant, the term in Einstein's equations that governs the expansion rate of space itself. Physicists calculated what this value should be based on quantum theory. What they got was a number that differed from the actual measured value by 120 orders of magnitude. That's not a rounding error. That's not an experimental imprecision. 120 orders of magnitude is a discrepancy so enormous that it represents what many physicists have called the worst prediction in the history of science. The actual cosmological constant, the one our universe possesses, is almost incomprehensibly smaller than quantum field theory says it should be. And yet it is precisely what it needs to be for galaxies to form, for structure to emerge, for observers to exist. It sits in an almost miraculous sweet spot. There is no physical theory we currently possess that explains why. 3 traditional explanations have been offered for this fine-tuning, and none of them fully satisfy. The first is luck. We won a cosmic lottery so extreme that it essentially defies rational contemplation, and here we are as a result. This is technically possible. It is not an explanation. It's the intellectual equivalent of shrugging. The second is the anthropic principle. The observation that of course we find ourselves in a universe compatible with our existence, because we couldn't exist in one that wasn't. This is true, but it answers a different question. It explains why we observe fine-tuning. It doesn't explain why fine-tuning exists. The third is the multiverse. the possibility that there are an essentially infinite number of universes, each with different physical constants, most of them dead, a few of them compatible with life, and we find ourselves in a life-compatible one because that's the only kind we could find ourselves in. This is a genuine scientific hypothesis seriously considered, but it trades one mystery for a potentially larger one. To solve the problem of fine-tuning, it requires the existence of an infinity of unobservable universes. That's a heavy ontological cost. And then there's a fourth possibility, one that has been gaining traction not because it's provable, but because it fits. What if the constants are precisely configured because someone configured them? What if our universe isn't an accident, isn't a selection from an infinite ensemble, but a deliberate design? A programmed environment, its parameters set carefully and intentionally by someone who knew what they wanted to produce. This is what a designed simulation would look like from the inside. The physics would work, the chemistry would be possible, complexity and consciousness would be achievable outcomes. Everything that needs to be true for observers to emerge would be true, not by chance, by design. And when physicists run computational models varying the fundamental constants, they find something striking. Almost every variation produces a sterile, empty, or immediately collapsing universe. The parameter space that allows for observers, what cosmologists sometimes call the habitable zone of physics, is remarkably, almost shockingly small. We're not in a Goldilocks zone. We're in a Goldilocks zone inside a Goldilocks zone inside another Goldilocks zone, and that level of nested precision starts to look less like coincidence and more like intention. Now, fine-tuning doesn't prove simulation. It's compatible with the idea of a creator who is not a programmer. It's compatible with a deeper physics we haven't yet discovered that explains why the constants must take the values they do. But if you're already taking simulation theory seriously, if the logical case has already created a crack in your certainty about base reality, then fine-tuning stops looking like a puzzle and starts looking like a clue. Because if you were going to build a universe capable of running an ancestor simulation, this is exactly the kind of universe you'd build. You'd tune it. You'd give it the constants it needs. You'd make chemistry possible, stars inevitable, evolution probable, and consciousness achievable. You'd give it exactly what ours has. Now we need to go small, very small, smaller than cells, smaller than atoms, smaller than the particles that make up atoms. We need to go down to the level where physics stops behaving like physics and starts behaving like something else entirely. Something that, depending on how you look at it, looks a lot like a program running out of resolution. Quantum mechanics is the most precisely tested theory in the history of science. Its predictions have been confirmed to more decimal places than any other physical theory we've ever constructed. And at the same time, it is the most philosophically bizarre framework anyone has ever been asked to take seriously. It describes a world in which particles don't have definite properties until they're observed, in which a single object can exist in multiple states simultaneously until measurement forces it to choose one, in which two particles separated by any distance can remain instantaneously correlated with each other in ways that seem to violate every intuition we have about space and locality. It is deeply, productively weird. And the simulation hypothesis offers something that mainstream physics has struggled to provide, a coherent, intuitive explanation for why it is the way it is. Let's start with the most famous experiment in quantum mechanics. You take a single electron, just one, and you fire it at a barrier with two small openings. What happens? If an electron was simply a tiny ball, a miniature bullet, you'd expect it to go through one opening or the other and hit the screen behind it at a corresponding point. That's not what happens. Instead, the electron creates what's called an interference pattern, a banded distribution across the screen that's characteristic of waves, not particles. The electron somehow goes through both openings at once, interfering with itself, as though it were a ripple in a pond spreading out in all directions rather than a marble flying in a straight line. But here's where it gets stranger. If you set up a detector to observe which opening the electron actually went through, if you try to catch it in the act, something changes. The interference pattern vanishes. The electron goes through one opening or the other, just like a normal particle would. The moment you look, reality crystallizes. The moment you look away, in a sense, it goes fuzzy again. It seems as though the act of observation, the act of the universe being required to produce a definite answer, changes the outcome. Physicists have been arguing about what this means for nearly a century, and there is still no consensus. But there's a perspective from simulation theory that handles it rather cleanly. If the universe is a computational system, rendering every particle's precise properties at every moment would be enormously expensive, wasteful even. What if the system doesn't bother? What if particles exist in a kind of compressed, undefined state, a superposition, a blur of possibilities, until something in the system requires a definite value, until an interaction demands that the program commit to an answer? The universe, on this view, is doing something very similar to what modern video games do with rendering. In real-time graphics, the engine doesn't render everything at full resolution simultaneously. Objects in the distance are simplified, low-detail approximations. Things outside your field of view aren't rendered at all. Full detail is reserved for what you're directly looking at, what requires the system's attention right now. The universe seems to work similarly. Particles don't have definite positions, definite spins, definite properties, until something forces the issue. Until observation, or more precisely interaction, requires specificity, then the system runs the calculation and locks in a result. What we call wave function collapse might simply be reality loading. Then there's quantum entanglement. Two particles created together in a particular way share a quantum state. Separate them by any distance you like. Put one in a laboratory in Geneva and send the other to the far side of the galaxy, in principle. And when you measure a property of one, the other instantly reflects the corresponding property, instantaneously, faster than light, across any distance. Einstein found this so troubling that he refused to accept it. He called it spooky action at a distance and spent years trying to argue it away. But we now know, through careful experiments, through technologies like quantum computing that are built on this very phenomenon, that entanglement is real. It works. Distance, in some sense, doesn't interfere with it at all. This violates every classical intuition about how information travels. Nothing should move faster than light. No signal should be able to bridge any distance instantaneously, and yet entanglement does exactly that. Within the framework of conventional physics, the explanation is subtle and somewhat unsatisfying. The particles share a quantum state. There's no signal being transmitted. No information technically travels faster than light. But it remains deeply strange. From the perspective of simulation theory, however, it becomes almost obvious. In a computational system, two objects don't have a fundamental spatial relationship. They're both entries in the same data structure. They're both part of the same program. The distance between them in the simulated environment is a rendered feature, an interface, not an architectural reality. Of course, changing one entry instantly affects the correlated entry. They're not actually separated by space. They're connected at the level of the code beneath space. Distance is the surface, correlation is the structure, and the structure doesn't care how far apart the surface positions are. There's also something called the measurement problem, which is perhaps the deepest conceptual puzzle in all of physics, and it sits right at the heart of why quantum mechanics is so philosophically disturbing. Before a measurement, a quantum system doesn't just have an unknown state, it has no definite state at all. It exists in what's called a superposition, a simultaneous overlap of all possible states, described mathematically by a probability wave. The electron isn't at an unknown location, it's at all possible locations at once, weighted by probability. It's not that we don't know where it is, it's that where it is isn't a fact yet. Only measurement collapses this wave into a single definite outcome. But what counts as measurement? Does the universe know when it's being observed? Does consciousness play a special role in collapsing quantum states, as some interpretations suggest? Or is any physical interaction sufficient? Does a detector collapse the wave function, or only a conscious observer? Physicists have genuinely debated this for 100 years without resolution. But the simulation framework offers something tidy. Measurement is any event that requires the simulation to commit to a value. Any interaction that forces the program to resolve a probability into an actuality. Consciousness isn't special, detectors aren't special. What's special is the demand for specificity, and the system responds to that demand by running the relevant calculation. The universe is, in a certain sense, computationally lazy. It doesn't calculate what it doesn't have to. It keeps things undefined, probabilistic, wave-like, until something demands otherwise. Then it resolves. Then it renders. It's not that quantum mechanics is weird. It's that quantum mechanics is exactly what you'd expect from a system that's optimizing its resource usage, and the optimization is elegant. Below a certain scale, what physicists call the Planck length, approximately 10 to the minus 35 meters, space itself stops having any meaningful definition. You cannot measure anything smaller, you cannot resolve anything finer. The fabric of space is quantized at that level, granular, pixelated in the most literal physical sense. There is a minimum unit of space, there is a minimum unit of time. The Planck time, roughly 10 to the minus 44 seconds, below which temporal intervals become physically meaningless. The universe has a resolution limit, and that resolution limit looks, in a way that's difficult to dismiss entirely, like the pixel size of a screen. Every simulation requires constraints. Without them, the system breaks. Information would loop back on itself. Causes would follow effects. Paradoxes would proliferate. If you were designing a universe, one of your first architectural decisions would be this: how fast can information travel? How quickly can cause produce effect? You'd need a hard ceiling, an inviolable maximum. Below that ceiling, the simulation remains consistent. Above it, everything falls apart. Our universe has exactly that. The speed of light, 299,792,458 meters per second, is not just the speed at which light travels, it's the speed of causality itself. It's the fastest rate at which any event can influence any other event anywhere in the universe. Nothing exceeds it. Not spaceships, not information, not gravitational effects. It is the absolute upper limit of how quickly the universe can update itself. The standard physical explanation for this, rooted in Einstein's relativity, is genuinely beautiful. Space and time are woven together into a single fabric, space-time, and the speed of light is the conversion factor between them. When you move through space, you move slightly less through time, and vice versa. The speed of light emerges from the geometry of space-time itself. It's not imposed from outside, it's an intrinsic feature of the structure. But here's the question that relativity elegantly sidesteps. Why does causality have a speed limit at all? Why isn't information transfer instantaneous? Why is the universe structured such that there is a ceiling on how quickly any event can affect another? The simulation framework offers an answer that is, depending on your comfort with the idea, either deeply satisfying or deeply unsettling. The speed of light is a processing rate. It's the maximum speed at which the simulation can propagate updates through its spatial grid. The universe isn't infinite in computational power. It has to manage resources. It has to ensure that cause precedes effect, that the timeline doesn't corrupt, that the simulation remains internally consistent. Capping information propagation at a fixed maximum speed achieves all of this. Think of it as bandwidth throttling. The simulation can only update so many cells per unit of time. Events propagate outward from their origin at this maximum rate. Nothing outruns the update cycle. This is why you can never send a message to your own past. Not because the universe is squeamish about paradoxes, but because the architecture doesn't permit it. The code won't allow it. Causality isn't a feature of physics that happens to prevent time travel. Causality is load-bearing infrastructure. Break it, and the simulation doesn't just malfunction, it crashes. And this perspective actually illuminates one of the stranger predictions of relativity: time dilation. The faster you move through space, the slower time passes for you relative to a stationary observer. Approach the speed of light and time almost stops. Why? The conventional answer involves the geometry of space-time. Motion through space and motion through time are inversely related. You're always moving through space-time at light speed. It's just a question of the split between spatial and temporal components. That's correct, as far as it goes. But consider this alternative framing. Moving objects are computationally expensive. The simulation has to track their position, velocity and interactions, update their fields, propagate their effects. The faster an object moves, the more calculations the system has to perform per unit of the simulated timeline. Time dilation could be a form of load balancing. Fast-moving objects receive fewer clock cycles. From their own frame of reference, time slows, because the system is already dedicating significant resources to processing their motion. This isn't a contradiction of relativity, it might be a computational underpinning of it. A reason why the geometry works out the way it does. And then there are black holes. The regions of space-time where the density of matter becomes so extreme that the curvature of space becomes infinite, where the physics we know breaks down, where the equations produce singularities, infinities that signal the failure of the mathematical framework. Black holes have event horizons, boundaries beyond which information cannot escape, cannot propagate, cannot influence the outside universe in any way. The singularity is censored behind this informational barrier. From the outside, you can never observe what happens inside. This is sometimes called cosmic censorship. The universe hides its own breakdowns. From the perspective of simulation theory, that's exactly what you'd want. Regions where the math fails, where the computation becomes undefined, are quarantined behind barriers that prevent the rest of the simulation from accessing the error. The singularity is a bug. The event horizon is the exception handler. The simulation catches its own failures and hides them behind boundaries, keeping the rest of the program running smoothly. Every strange feature of relativity, the speed limit, time dilation, event horizons, makes sense as a form of computational management. Not as proof, not as evidence that requires no alternative explanation, but as a consistent, coherent pattern. The universe behaves like a system that is managing its own computational constraints. And that pattern, once you start seeing it, is difficult to unsee. There's a mystery that lives right at the heart of physics, one that's so familiar that most scientists have stopped noticing how strange it is. Mathematics works. Not just works perfectly. Every time we look at the universe at any scale, in any direction, under any conditions, we find mathematical structure waiting for us. Precise, elegant, compressible mathematical structure. Maxwell wrote down his equations for electromagnetism in the 19th century, and embedded in those equations was the prediction that electromagnetic waves travel at exactly the speed of light. When physicists measured the speed of light, the number matched Maxwell's prediction. We then discovered that light itself is an electromagnetic wave. The math came first. Reality confirmed it later. Dirac wrote down a relativistic equation for the electron in 1928, and his equation required the existence of a particle identical to the electron but oppositely charged. At the time, no such particle was known to exist. 4 years later, the positron, the electron's antimatter twin, was discovered in cosmic ray experiments. The equation knew before the experiments did. Einstein's general relativity predicted the existence of gravitational waves, ripples in the fabric of space-time produced by violent cosmic events, decades before we had any technology capable of detecting them. When we finally built instruments sensitive enough, in 2015, the waves were right where Einstein's mathematics said they'd be. Why does this keep happening? Why does mathematics, a system humans developed to count, to measure, to organize thought, keep turning out to be the secret language of physical reality? The physicist Eugene Wigner wrote an essay in 1960 called The Unreasonable Effectiveness of Mathematics in the Natural Sciences, in which he named this as a genuine mystery. Mathematics, he pointed out, is not designed to describe physics. It's developed by mathematicians following rules of internal logical consistency, often with no physical application in mind, and yet it consistently, repeatedly, inexhaustibly describes the deep structure of the physical world with uncanny precision. Wigner found this bordering on the mysterious and said there was no rational explanation for it. That was 65 years ago. We still don't have a fully satisfying answer. One physicist who has taken the question most seriously is Max Tegmark at MIT. Tegmark's proposal, what he calls the mathematical universe hypothesis, is radical in a way that's easy to underestimate. He doesn't argue that mathematics describes reality particularly well. He argues that physical existence and mathematical existence are the same thing. The universe isn't written in mathematics. The universe is mathematics. Physical reality is a mathematical structure, and mathematical structures that are sufficiently complex don't merely resemble reality, they are reality. On this view, asking why the universe obeys mathematical laws is like asking why a circle is round. The question dissolves. The universe is mathematics in the same way that circles are circular. It's definitional. Now, Tegmark's hypothesis sits at the outer edge of what most physicists are willing to entertain, but it matters enormously to the simulation argument. Because if the universe is fundamentally mathematical, it is also fundamentally computational. Mathematics and computation aren't different things. Computation is applied mathematics. Every algorithm, every program, every simulation is executing mathematical operations. When you simulate a physical system, you're not building a representation of mathematics in silicon. You're extending the same mathematical fabric into a new substrate. If our universe is mathematical at its core, then the distinction between real universe and simulated universe might be less meaningful than we assume. The math is the math, wherever it runs. And the mathematics we find in our universe isn't arbitrary, it's specific, it's compressed. The laws of physics, all of them, governing everything from subatomic particles to the largest structures in the cosmos, can be written down in equations short enough to fit on a blackboard. In some cases short enough to fit on a t-shirt, as physicists are fond of demonstrating at conferences. Why should fundamental reality be this simple? Why should the deep structure of the universe be expressible in compact form? Think about what it would mean if the universe weren't like this. Imagine a cosmos where every particle's behaviour was governed by its own idiosyncratic rules, where no general law captured more than a single case, where the universe was irreducibly complex at every scale. That universe would be impossible to simulate. You'd have to hard-code every interaction individually. But our universe isn't like that. Our universe has general rules, elegant, symmetric, compressible rules, from which the complexity of everything else emerges. That's not just convenient for physicists, it's convenient for programmers. It's the architecture of a well-designed system. You don't hard-code the behaviour of every individual molecule. You write the rules of chemistry, and chemistry handles the molecules. You write the rules of physics, and physics handles the chemistry. You write as little code as possible, and let the emergent complexity do the rest. Our universe looks like it was built by someone who understood good software design. And then there's the question of discovery versus invention. When mathematicians prove new theorems, Are they discovering truths that existed before the proof, timeless structures waiting to be found? Or are they inventing new structures, bringing them into being through the act of thinking? Most mathematicians, when asked, say they feel like discoverers. They feel like explorers of a landscape that was already there. The Mandelbrot set, that endlessly complex fractal shape that you can zoom into forever, finding infinite detail at every scale, wasn't invented by Benoit Mandelbrot. It was discovered. The structure was always there, implicit in the mathematics, waiting for someone to look. This matters for the simulation hypothesis in a specific way. If mathematical structures are real, independent of whether any physical system is instantiating them, if the Mandelbrot set existed before Mandelbrot found it, and will exist after every computer capable of rendering it has long since turned to dust, then computation is not just a physical process, it's a mathematical reality, and a sufficiently complex mathematical structure that includes observers, minds that experience being inside the structure, might be as real as anything else. This is the direction Tegmark's thinking leads, and it's the direction that makes the simulation hypothesis less about hardware, and more about something deeper. Less about, is there a computer running our universe? And more about, is the universe a mathematical object that is being, in some sense, computed? These are different questions, and the second one is harder to dismiss. In the 1990s, a set of ideas emerged in theoretical physics that were so strange, so counterintuitive, that even the physicists developing them took some time to fully accept what they implied. The holographic principle, the idea, initially proposed by Gerard 't Hooft and later developed by Leonard Susskind, and formalised most precisely by Juan Maldacena, is this. All the information needed to describe everything happening inside a volume of space can be completely encoded on the two-dimensional surface that bounds that volume. Not approximately, exactly. The three-dimensional interior is, in a precise mathematical sense, a projection of the two-dimensional boundary. Reality, in other words, might be holographic. You might have seen a hologram, one of those images on a credit card or a piece of glass that appears three-dimensional when you look at it but is printed on a flat surface. The three-dimensional image is encoded in a two-dimensional pattern of interference. All the depth, all the volumetric detail, emerges from what is fundamentally a surface. The holographic principle suggests the universe might work the same way. What we experience as a three-dimensional reality, with volume and depth and objects that exist at different distances from us, might be the projection of information encoded on a two-dimensional boundary. The depth might be emergent, the volume might be derived. The experience of living in three-dimensional space might be, in a specific technical sense, a holographic illusion. Now, it's important to be precise here. The holographic principle as developed in physics is not a claim that the universe is a simulation. It's a claim about the mathematical equivalence between descriptions of gravity in certain spaces and descriptions of quantum field theories on the boundaries of those spaces. It was initially developed in the context of string theory and anti-de Sitter space, a particular kind of curved space that doesn't precisely describe our universe. But the implications have been taken seriously far beyond their original technical context. Because what the holographic principle says, at a fundamental level, is this. The apparent dimensionality of reality is not necessarily the same as the underlying dimensionality of reality. What you experience might be the rendering. What's actually going on might be a lower dimensional encoding. And if you're thinking about simulations, that's a fascinating framework. In a simulation, the rendered image and the underlying data are never the same thing. The three-dimensional environment you move through in a virtual world doesn't exist as a three-dimensional thing in the computer's memory. It exists as numbers, as data structures, as a mathematical encoding from which the three-dimensional experience is generated on the fly. The experience and the underlying reality are always at different levels. The holographic principle says something similar might be true of the actual universe. What we experience as space, as volume, as depth, as three-dimensional existence might be a rendering from a two-dimensional informational substrate, not a simulation in the trivial sense of someone is running software, but a universe in which the architecture of experience is already separated from the architecture of information. Already, at the deepest physical level, organised more like a display than like a thing. The physicist John Wheeler, who worked with both Einstein and Bohr, and who gave us the term black hole, spent the later decades of his career developing what he called the it from bit hypothesis. His proposal was that at the most fundamental level, reality is not made of matter or energy, but of information. Physical things, particles, fields, forces, are not the primitive constituents of the universe. Information is. It from bit means every physical thing derives its existence from answers to yes or no questions, from binary choices, from the fundamental currency of computation. Matter is what information looks like when it organizes itself into stable patterns. Space is what information looks like when it spreads out. Time is what information looks like when it changes. On this view, the universe isn't just described by information. The universe is information. And a universe made of information, a universe that is, at its foundation, computational, is a universe for which the simulation hypothesis stops being exotic, science fiction, and starts being a description of the architecture. We've been circling something for a while now, and it's time to come at it directly. Because any serious engagement with the simulation hypothesis has to eventually ask the question that matters most to you personally. Not is the physics simulated, but am I simulated? Is the thing reading these words, the awareness behind your eyes, the felt sense of being present in this moment, is that a genuine independent phenomenon, or is it a process running in code? Is consciousness simulated, or is it something that exists outside any possible simulation? This is, without question, the most contested part of the whole discussion. The deepest philosophers, the sharpest physicists, and the most careful neuroscientists have been circling the nature of consciousness for decades, centuries, if you count the philosophers who came before the scientists. And the honest answer is that we don't have a complete picture. We have partial answers. We have suggestive frameworks. We have a growing understanding of the neural correlates of consciousness, the brain states that accompany specific conscious experiences. But we don't have an explanation for why there is experience at all. Why is there something it's like to be you, rather than nothing? Why doesn't your brain process information in the dark without the accompanying inner light of subjective experience? This problem, what the philosopher David Chalmers calls the hard problem of consciousness, remains genuinely unsolved, and the simulation hypothesis interacts with it in a way that's simultaneously clarifying and deepening. Chalmers himself has thought about this carefully. His argument goes something like this. If we are in a simulation, the question of whether simulated minds have genuine consciousness depends entirely on whether consciousness is substrate independent. If consciousness is what the brain does, if it's a process, a pattern, a particular kind of information processing, then a sufficiently detailed simulation of that process would produce real consciousness, not a representation of consciousness, not a convincing imitation, actual experience, actual subjectivity, actual presence. Because there's nothing special about the biological neurons that produce your consciousness that couldn't in principle be reproduced in a different physical substrate, as long as the relevant information processing patterns are the same. This is the view called functionalism, and it's held by many philosophers of mind. On this view, you could be simulated and still be genuinely conscious. The simulation doesn't make your experience less real. It just means your experience is running on different hardware than you thought. But there's a competing view. The philosopher and mathematical physicist Roger Penrose, along with the anesthesiologist Stuart Hameroff, has argued that consciousness isn't simply a computational process. Their orchestrated objective reduction theory proposes that consciousness emerges from quantum mechanical processes in the microtubules inside neurons, processes that are inherently non-computable, that depend on physics at a level no classical computer could replicate. If Penrose and Hameroff are right, then a classical simulation, even an extraordinarily detailed one, couldn't produce genuine consciousness. It could simulate the outward behaviour of consciousness without generating actual experience. The lights would appear to be on from the outside. Inside, there would be nothing. More recently, a team of researchers at UBC Okanagan published a paper arguing along related lines, using Gödel's incompleteness theorem to argue that reality requires a kind of understanding that is fundamentally non-algorithmic, that the foundations of the universe depend on processes that no computation can fully capture. If true, this would mean that any simulation running inside our universe would necessarily be less than our universe, missing something that exists at the substrate level and cannot be replicated in code. This is a serious argument, and it deserves to be taken seriously. But it also has a significant limitation that critics have pointed out. The argument applies to simulations running on computers built from the same physics as our universe. It says nothing about what might be possible on the hardware running our universe. The system that simulates us, if there is one, doesn't have to obey our physics. It doesn't have to obey our logic. Its computational capacities might be as far beyond our understanding as quantum mechanics would be beyond the understanding of a medieval scholar. We can't constrain the capabilities of the simulator using the limits of the simulated, and so consciousness remains the most open question in all of this. It might be computational, in which case simulated minds are genuine minds, and your inner life is as real as reality gets. It might be non-computable, in which case a simulation might be a philosophical zombie, behaviourally indistinguishable from a conscious being but experiencing nothing. Or, and this is the possibility that I find most intriguing, the question itself might be dissolving. Because if the universe is fundamentally mathematical, if information is the primitive substrate of existence, then the distinction between a real mind and a simulated mind might be less meaningful than it seems. A mathematical structure that includes something that functions as consciousness might simply be a conscious mathematical structure, running or not running, instantiated or not instantiated. The experience might be a property of the structure, not of the hardware. Here is where the science gets genuinely current. Not historical curiosity, not philosophical thought experiment, but active research being conducted right now by physicists working at the intersection of information theory and fundamental physics. Over the past decade and a half, a growing number of scientists have begun taking seriously the idea that information is not merely a useful description of the universe, but a fundamental constituent of it. And some recent developments have added specific, testable content to that broader intuition. In 2023 and 2024, a physicist named Melvin Vopson at the University of Portsmouth published a series of papers proposing what he calls the second law of infodynamics. The standard second law of thermodynamics, the one every physics student learns, says that entropy in an isolated system tends to increase over time. Disorder grows, complexity dissipates, things fall apart. This is why your coffee goes cold and your room gets messy, and the universe tends toward uniformity over long timescales. But Vopson's research proposes that information systems in which information is the primary currency, might behave differently. In information systems, he argues, entropy tends to decrease rather than increase. Information systems self-organize, self-optimize, compress. They become more ordered, not less, over time. The biological world shows exactly this. DNA is extraordinarily compressed information. The process of evolution doesn't produce random noise. It produces increasingly refined, increasingly efficient biological organisms. The universe's tendency toward biological complexity appears to run against the thermodynamic grain, and the second law of infodynamics offers an explanation. Biological systems are information systems, and information systems obey a different entropy law. Bostrom takes the next step explicitly. A universe whose behaviour is consistent with the second law of infodynamics looks like a computational system, one that is actively optimizing its own information structure, not running down toward equilibrium, running toward compression and efficiency. The genetic code compresses vast information into minimal space. The laws of physics are compressible into elegant equations. The universe's most complex structures, minds, ecosystems, civilizations, are information-dense entities that emerge from simpler substrates through processes that increase rather than decrease local order. If the universe is a simulation, this is what we'd expect. Simulated systems optimize their information representation. They use elegant rules rather than brute force. They produce complexity through compression. And the universe, observed from this angle, looks precisely like a system that is doing exactly that. This is not yet a settled scientific claim. Bostrom's framework is controversial and actively debated. But the direction of travel is significant. Physicists are increasingly willing to entertain the idea that information isn't just a way of describing the universe. It might be what the universe is made of. And a universe made of information is a universe for which computation is not a metaphor. It's a description. Seth Lloyd at MIT has taken a related approach. His work, particularly in a paper titled Ultimate Physical Limits to Computation, calculates the maximum amount of information the observable universe could ever process, given its mass and age and the laws of thermodynamics. The number is astronomical, on the order of 10 to the power of 90 calculations since the Big Bang. But it is finite. The universe, as a computational system, has a finite total throughput. It has processed an enormous number of operations, but not an infinite number. This is, in a subtle way, consistent with the existence of computational constraints. A simulated system has limits. Our universe appears to have limits. The Planck scale, the speed of light, the finite total entropy. These aren't just features of physics. They might be the specifications of a machine. And then there is the holographic information bound, sometimes called the Bekenstein bound, which states that the maximum amount of information that can be contained in any given region of space is proportional not to its volume but to its surface area. This was originally derived from the thermodynamics of black holes, but it applies to any bounded region of space. Counterintuitively, you can't fit more information into a larger volume by making it bigger. You can only fit more information in by making the boundary larger. The amount of information in a region scales with the square of its size, not the cube. This is deeply strange from the perspective of ordinary physics, where you'd expect more volume to mean more room for stuff. But it's completely natural from the perspective of information theory. It's exactly how a hologram works. The depth is derived from the surface, and it's exactly how a simulation would work. The rendered three-dimensional environment contains only as much information as the underlying two-dimensional data structure. The display is rich, but the data is bounded. It would be dishonest and frankly uninteresting to present only the case for the simulation hypothesis. The honest engagement with this idea requires looking directly at the strongest objections, understanding what they actually say, and deciding whether they undermine the hypothesis or merely constrain it. There are several serious counter-arguments, and they deserve careful treatment. The first and most direct objection is the one made by the physicist Sabine Hossenfelder, who's been one of the most articulate critics of simulation theory in recent years. Her argument has two parts. First, she argues that the hypothesis is scientifically empty, that it makes no predictions that could be tested and falsified, and that a theory that cannot be falsified isn't really a scientific theory at all. It's philosophy, or speculation, or, as she's put it bluntly, pseudoscience. This is a serious charge. Science advances through falsification. through making predictions and then checking them against observation. If the simulation hypothesis predicts the same observable universe, regardless of whether it's true or false, then science has nothing to say about it. It lives in a domain beyond the reach of the scientific method. The second part of Hossenfelder's argument is more technical. She contends that simulating the universe at the level of detail that would be required to produce the experience we have, down to the quantum scale, down to the Planck length, would require a computational system so vast that it would itself require more matter and energy than the observable universe contains. You can't fit the computer inside the system being simulated, at least not if both obey the same physics. This is a compelling argument, and it's consistent with recent astrophysical work, including a 2025 paper by the cosmologist Franco Vazza at the University of Bologna, which calculated that simulating even a low-resolution version of the Earth, consistent with the highest energy neutrino observations, would require computational resources that are physically implausible, given what we know about the information-energy relationship in our universe. But, and this is crucial, these arguments assume that the simulator is constrained by the same physics as the simulated. They assume that whoever or whatever is running our universe must be operating within our physics. This assumption may not be valid. If the universe we experience is a simulation, it's being run on hardware operating under a different set of physical laws entirely, laws that may permit computational densities, processing speeds, and informational architectures that are simply beyond our ability to imagine or constrain. The computer running our simulation doesn't have to fit inside our universe. It exists in a different layer of reality. Our physics applies to the simulation, not to the simulator. This doesn't mean the objection is wrong. It means the objection applies to a specific class of simulation arguments, ones where the simulator is constrained by our physics, and leaves open the broader question of whether a simulation by an entity operating under different physical laws is possible. Another serious objection comes from the physicist George Ellis, who described the simulation hypothesis as totally impracticable from a technical viewpoint, and suggested it belongs more to late-night philosophical speculation than to rigorous science. He's not alone. Many physicists who work in the area of quantum gravity, string theory, and related fields find the hypothesis a distraction, an interesting thought experiment that doesn't connect to the real unsolved problems of physics in any productive way. Sean Carroll at Caltech has made a related point. He argues that even if you're in a simulation, the physics of your simulated world is the physics that matters to you. You're made of simulated matter, experiencing simulated forces in a simulated environment. For all practical purposes, for every measurement you could ever make, every experiment you could ever conduct, the simulation is indistinguishable from base reality. And if it's indistinguishable in principle, what does it mean to say it's less real? Carroll's point is that the simulation hypothesis might be metaphysically interesting but scientifically sterile, because it can never affect how we do physics or what we predict. These are genuinely important challenges, and they don't have clean rebuttals. The simulation hypothesis is not a scientific theory, in the same way that general relativity is a scientific theory. It doesn't generate precise testable predictions that distinguish it from its competitors. It's more like a framework, a way of interpreting the features of reality that we do. Observe, suggesting that those features are consistent with a particular kind of underlying architecture. That's philosophically interesting. It may even be scientifically suggestive, but it isn't the same as providing evidence in the traditional scientific sense. What keeps the hypothesis alive despite these objections is the logical force of Bostrom's trilemma and the absence of a clearly better alternative, not because the other options have been ruled out, they haven't, but because none of them are comfortable either. You're choosing between extinction, universal indifference, and simulation. And the logic of probability, combined with our intuitions about curiosity and the likelihood of technological development, keeps pulling attention toward the third option. Now let's slow down. We've been moving through physics and logic at a particular pace. We've been following evidence and arguments and counter-arguments, chasing the intellectual thread wherever it goes. And that thread has brought us somewhere interesting. Not to a definitive answer, the question doesn't have one yet, but to a place where the question itself has weight, where sitting with it, rather than rushing past it, seems like the right thing to do. Because there's a philosophical dimension to all of this that the physics and the mathematics can describe, but can't fully contain. And it's worth spending some time there. Here's the question that actually matters to you and to me. The one that isn't about physics constants or quantum wave functions, but about life. If we are in a simulation, if this is all constructed, if the universe we experience was designed by an intelligence outside our reach, what does that mean? Does it change anything? Does it make your life more or less significant? Does it make the people you love more or less real? Does it make the grief you felt, the joy you've experienced, the moments that have shaped who you are? Does it make those things matter more or less or differently? The instinctive answer for many people is that it would be devastating. That learning we're simulated would be like learning that everything we've ever known is fake, that the ground beneath us is false, that our experiences have no genuine substance, that we've been, in some sense, deceived. But I want to push back on that instinct gently, and I want to do it not by dismissing it. The instinct is natural, and it comes from a deep, legitimate place, but by examining the assumption underneath it. The assumption is that simulated experience is less real than non-simulated experience. That because the substrate is different, because what produces your thoughts and feelings and perceptions is code running on hardware, rather than neurons running on biochemistry, the content of those thoughts and feelings and perceptions is somehow diminished. But is it? Your love for the people in your life, is it diminished if it arises from carefully arranged patterns of information, rather than from electrochemical signals in biological tissue? Is your experience of beauty less beautiful if the photons triggering it are rendered rather than emitted? Is your pain less painful, your wonder less wondrous, your curiosity, right now, working through these ideas, less genuine? The philosopher David Chalmers has made this point with characteristic precision. If you are a simulated mind with genuine subjective experience, if there is something it's like to be you, and there clearly is, then your experience is as real as experience gets. The medium doesn't determine the validity of the content. A story told in ink is not less meaningful than a story told in paint. A truth realized in a dream, upon waking, is still a truth. You're not less yourself because you might be code. And here is something else worth sitting with. If we are simulated, we are not alone in the simulation. Every person you have ever loved, every stranger you've ever passed on the street, every mind you've ever encountered, they're simulated too. The simulation isn't a trick played on you. It's the environment you share with every other conscious being in your world. Your suffering is theirs. Your joy is theirs. The relationships you've built, the histories you share, the culture you've inherited and contributed to, all of it is real within the terms of the simulation. And within those terms, it may be as real as anything in base reality. Perhaps more real, in the sense that matter's not physically primary, but experientially present. There is one more thread we haven't pulled on yet, and it's the one that, for many people, makes the simulation hypothesis feel most emotionally charged. If we're in a simulation, if something or someone built this, what does that say about the nature of that something? What does it say about the relationship between the simulated and the simulator? And is there any meaningful sense in which we could communicate with, or be in relationship with, whatever constructed our reality? Let's be precise about what the simulation hypothesis does and does not say here. It does not say that the simulator is benevolent or omniscient in any theological sense, or interested in your well-being, or aware of you specifically as an individual. A programmer who builds a complex virtual world and populates it with simulated minds is not automatically in a relationship with each of those minds. The minds might be running in the background, their experiences unobserved, their outputs simply part of the data the simulation is generating. The simulator might be a post-human civilization studying its own past. It might be a research institution. It might be an automated system that no longer has active human operators. It might be something so foreign to our conceptual vocabulary that none of our existing categories apply. What's interesting, though, is that the simulation hypothesis does have a specific thing to say about an old theological puzzle. The problem of evil, the question of why a good and omnipotent creator would permit suffering in the world, has occupied philosophers and theologians for millennia. Within the simulation framework, suffering doesn't require a malevolent or indifferent creator. It might simply be an emergent feature of a complex simulated environment, something that arises from the interaction of physical laws and evolutionary dynamics, not something deliberately designed. The simulator might be running an ancestor simulation to understand history, not to optimize for well-being. The suffering isn't a design feature. It's a side effect of fidelity. A simulation detailed enough to produce genuine historical data has to be detailed enough to include hardship. And there's something else. The simulation hypothesis makes possible a certain kind of meaning that secular materialism struggles with. In a purely material universe, one in which everything is atoms and forces and nothing more, the existence of consciousness, the existence of meaning, the existence of the felt sense of significance that colours human experience. These things are accidents, byproducts of matter organised in a particular way with no intrinsic significance of their own. But in a simulated universe, consciousness might be the point. The simulator, whatever it is, had to choose what to simulate. It chose a universe capable of producing observers. It chose parameters fine-tuned for complexity, for biology, for minds. Whatever the reasons, minds were on the menu. That's not the same as saying minds are sacred, or that the simulator cares about you. But it does mean that consciousness isn't an accident in this framework. It's a feature. It was built in. And there is in that a quiet kind of significance, not comfort exactly, not the warm reassurance of traditional religious frameworks, something cooler and stranger. The sense that whatever you are part of something that was designed to include something like you. Whether you find that reassuring or unsettling might tell you something about yourself. Now there's a question that follows from this, and it's one that physicists and philosophers have been circling for years. If the simulator chose to build our universe, if they set the constants, initialized the conditions, and started the program running, is there any way to contact them? Any channel through which information could flow from the simulation to the host layer? The honest answer is, we don't know, and the question might not even be well formed. A simulated mind communicating with the simulator would be a bit like a character in a novel trying to communicate with the author. The character exists within the story. The author exists at a different level of reality. The story's physics, its rules, its constraints, don't apply to the author. There's no mechanism within the story by which the character could send a message that crosses the level boundary. And yet, and this is where it gets interesting, there might be exceptions. If the simulator is observing the simulation, if it's monitoring the outputs, then the simulation's behaviour is a form of communication. Not intentional perhaps, but legible. A civilization that starts asking serious questions about whether it's simulated, that starts building the conceptual frameworks to understand its own constructed nature, might be doing something that registers in the host layer, not because the simulation has found a channel, but because the simulation's outputs have become interesting in a new way. We might be watched, not because we are individually significant, but because we are collectively doing something that no previous stage of the simulation produced. We are asking whether we are simulated. We are building the intellectual tools to investigate our own potential constructedness. And if the simulator is a civilization that built this as an ancestor simulation to study its own past, that fact, the fact that we are now asking this question, might be exactly the kind of data they were looking for. We might, in that sense, be approaching the edge of the story, not breaking through, not communicating directly, but becoming legible. One of the more practically interesting questions that arises from simulation theory is this: if we are simulated, would there be detectable evidence? Not philosophical evidence, not mathematical elegance, not conceptual fit, but actual physical evidence. Glitches in the matrix, discontinuities in the rendering, signatures in the data that would only be present if our universe is running on a finite computational substrate. In 2012, physicists Silas Bean, Zoe Davoudi, and Martin Savage at the University of Washington published a paper that attempted to do exactly this, to identify what observational signatures a simulated universe might have. Their approach was based on the following reasoning. If the universe is being simulated on a computational grid, if space is discretized into units at some fundamental scale, as our Planck length argument suggests, then that lattice structure would leave detectable marks on the behavior of high-energy particles. Specifically, it would impose an anisotropy, a preferred direction, on the distribution and energy spectrum of high-energy cosmic rays. Particles moving along the axis of the computational grid would behave differently from particles moving diagonally through it. You'd see a pattern in the data that reflected the underlying grid architecture. The team didn't claim that such a pattern exists. They identified what it would look like if it did, and noted that with sufficiently precise measurements of cosmic ray data, we might be able to test for it. To date, no such pattern has been conclusively identified, but the available data doesn't rule it out either. The measurements required are at the edge of current technological capability. This is science still in progress, and there are other potential signatures. This second law of infodynamics, as proposed by Vopson, predicts that if information is a fundamental physical quantity, with mass, with gravitational effects, then extremely sensitive measurements of mass changes in atomic systems undergoing information erasure might be able to detect it. If information has mass, that's a measurement that could in principle be made. Vopson has proposed specific experimental protocols for testing this. The experiments haven't yet been conducted with sufficient precision, but they are physically possible. These are not the dramatic glitches of Hollywood science fiction. They're not flickering pixels or déjà vu or moments when the laws of physics visibly malfunction. They're subtle statistical patterns in the distribution of cosmic rays, tiny mass changes in information systems, barely detectable signatures in the quantum noise of empty space. If they exist, they would tell us something profound. If they don't, that wouldn't disprove simulation. It would simply constrain the kind of simulation we might be in, ruling out the particular grid-based architecture Bean and colleagues were testing. The universe, as we've seen in every other domain of science, is willing to give up its secrets slowly, imprecisely, and only to those patient enough to look in exactly the right way. The simulation hypothesis is no different. There's a particular experience that I think most people have had, or something like it. A moment, often at night, often outdoors, often alone or nearly alone, when the scale of things becomes suddenly, briefly, viscerally real. You're looking at the sky, and for a moment you're not thinking about what you had for dinner, or what you said to someone this morning, or what you're planning for tomorrow. You're just there, present to the fact of the sky, to the fact of the stars, to the fact that you are an enormously complex arrangement of matter and energy that has somehow developed the capacity to look at itself and at the universe and to know what it's looking at. That moment of contact with scale, with the sheer size and age and complexity of what's out there, is one of the most consistently reported profound experiences across cultures, across centuries, across every kind of life. And what's interesting about it in the context of everything we've been discussing is that the simulation hypothesis doesn't diminish it. If anything, it deepens it. Because if the night sky is a simulation, if those stars are rendered textures in a program, the fact that you can look at them and feel something, the fact that the program is complex enough to produce not just stars but beings who find stars beautiful, that's more extraordinary than a cold, indifferent physical cosmos. Not less, more. The universe, whatever it is, has produced beings who are capable of wonder. That capacity, wonder, is not something that was required for survival. Evolution didn't need wonder. It needed fear, hunger, sex drive, social bonding. Wonder is, in a sense, extra. It's the overflow of a mind complex enough to have more attention than the immediate situation demands. And that overflow reaches upward, outward, backward, into time and forward into possibility and asks, what is this? Where does it come from? What am I doing inside it? If you are simulated and you're looking at a simulated sky and you feel wonder, that wonder is real. It is, in a meaningful sense, the most real thing in the scenario, because it is the thing that is actually happening, not the pixels, not the rendering, not the code, the experience, the feeling, the aliveness. That is what is genuinely occurring, and nothing about being simulated changes that. Nothing can reach inside the experience and make it less. The experience is what it is. Right now, wherever you are, whatever hour it is, whatever state of wakefulness or drowsiness you're in, there is something it is like to be you. There is a felt quality to your existence, an inner texture, a sense of presence. That is not in doubt. That is the one thing that can't be taken away. Descartes was right about that much, even if he didn't know about computers. You think, you feel, you wonder. Therefore you are. Real or rendered, that's the fact on the ground. That's the starting point and the ending point of everything. Let's come back to information one final time because it's where several of the threads we've been following converge. John Wheeler, It from Bit. Max Tegmark, Mathematics is Reality. Melvin Vopson, The Second Law of Infodynamics. Seth Lloyd, The Universe as Quantum Computer. These aren't 4 separate speculative ventures, they're 4 approaches to the same underlying question. What is the universe made of at the most fundamental level? Not quarks, not strings, not fields. What are those things made of? What is the substrate of the substrate? And the answer that keeps emerging from different directions through different methodologies is information. The universe appears to be, at its foundation, an information processing system. The matter and energy we experience are the outputs of this system. Space and time are the interface through which the outputs are presented to the observers inside it. The laws of physics are the code, the constants are the parameters, and the whole thing, the staggering, beautiful 13 billion-year-old cascade of structure and complexity and consciousness, is what happens when information is allowed to process itself at sufficient scale, for sufficient time, with sufficiently elegant rules. This doesn't settle whether we're simulated by an external intelligence. It suggests something more general and in some ways more profound. It suggests that the universe doesn't require an external simulator to be, in a meaningful sense, computational. It might be self-computing. It might be a mathematical structure that is its own simulation, running on no hardware except the mathematics itself, existing not because someone is running it, but because it exists. Because to be a consistent mathematical structure of this kind is to be real. This is where Tegmark's mathematical universe hypothesis intersects most productively with the simulation argument. The question, are we simulated, might be less about whether there's a computer somewhere and more about whether reality is fundamentally informational. And if it is, if information is genuinely the primitive constituent of existence, if bits come before things, if the universe is a self-running computational process, then the distinction between real and simulated might be dissolving into something more interesting. something more open, something that doesn't require us to choose between this is real and this is fake, but invites us to understand that real might mean something different than we assumed, that real might mean a consistent, self-referential information processing structure that contains observers who experience being inside it. That real might mean exactly this, exactly here, exactly now. There's one final observation I want to share because it feels like the most honest way to close this investigation. It's the observation that the simulation hypothesis is self-referential in a way that makes it uniquely strange among scientific and philosophical ideas. If we are simulated, then the intelligence that discovered that we might be simulated is simulated intelligence. The logic that built the trilemma is simulated logic. The mathematics that found patterns suggesting digital architecture is simulated mathematics. The consciousness pondering its own potential constructedness is simulated consciousness. And this creates a loop that is either the deepest possible irony or the deepest possible clue. Because a simulation that produces beings sophisticated enough to investigate whether they're simulated, a program complex enough to generate its own epistemology, is not a simple program. It is not a trivial system. Whatever is running this, if something is running this, created something with the capacity to turn its own instruments of understanding on its own most fundamental nature. And there's something in that capacity, in the reflexive, self-examining, endlessly questioning nature of human intelligence, that feels significant. Not because it proves anything, but because it suggests that whatever this is, it contains genuine depth, genuine interiority, genuine recursion. The universe produced beings who can ask whether the universe is real. That's extraordinary. Not because the question has an easy answer, but because the question is being asked at all. You are right now part of that extraordinary thing. You are the universe's capacity for self-reflection, operating in real time. Whatever you're made of, neurons, code, mathematics, or something we have no name for yet, that process is happening. That looking at itself is happening. And there is something in that that resists reduction. Something that feels from the inside like it matters. Like it's not just a calculation proceeding, but a genuine encounter. A genuine meeting between mind and world, wherever that world actually is and whatever it's actually made of. There's a kind of peace in genuine uncertainty, once you learn how to inhabit it. Not the restless uncertainty of someone who hasn't thought hard enough to know the answer. That's a discomfort waiting to be resolved. But the deeper uncertainty that arises after you have thought hard, after you've followed the evidence, after you've weighed the arguments, and arrived at the honest recognition that the question exceeds your ability to answer it. That uncertainty feels different. It's more settled somehow, more spacious. Because it isn't waiting to be resolved into a comfortable known. It's accepting of its own nature as unknown, and it finds a way to live well in that acceptance. The simulation hypothesis lives at that depth. It isn't the kind of question that will be resolved by the next experiment, or the next philosophical argument, or the next technological development in computing. It might never be resolved, not from inside the system that generated the question. And learning to sit with that, to find it interesting rather than threatening, to let it open your sense of what's possible rather than close down your sense of what's solid, is perhaps the most mature response to it. The great physicists who have grappled with the deep questions of quantum mechanics, Bohr, Heisenberg, Schrödinger, Feynman, had to learn something similar. They had to learn to work productively with a theory they couldn't fully interpret. Quantum mechanics told them things that were experimentally precise and philosophically opaque. It made predictions of extraordinary accuracy while refusing to yield a satisfying picture of what was actually happening at the fundamental level. And the physicists who did best were the ones who were comfortable with that, who could say, I don't know what the wave function really is. I don't know what collapse actually means. I don't know whether the universe is fundamentally deterministic or stochastic. But I know how to use the formalism, and I know what it predicts, and I know that those predictions are correct, that's enough to work with. The simulation hypothesis invites a similar posture. You don't need to know whether it's true to find it useful. You don't need to resolve it to let it inform how you think about consciousness, about information, about the nature of reality's foundations. The framework is productive regardless of whether it's factually correct, because it generates questions that are worth asking and prompts investigations that reveal genuine features of the world. And maybe that's the most honest place to land, not with a verdict, with an orientation, a way of holding the question that's neither credulous nor dismissive, neither convinced nor contemptuous, curious, carefully, patiently curious. The way you'd hold a beautiful and unsolved mathematical conjecture, the way you'd hold an unexplained pattern in the data, with interest, with attention, with the sense that this is something worth returning to, worth thinking about again tomorrow and the day after and whenever the right kind of quiet makes room for it. Let me come to where I want to leave you, not with an answer, with a few thoughts that might be good company in the days after this. The simulation hypothesis, in its deepest form, is not really a claim about computers. It's a claim about the nature of existence. It's the claim that what we experience as reality, the irreducible given of our lives, the world that shows up every morning when we open our eyes, might be a representation rather than the thing itself. That it might be, in a specific technical sense, at one remove from ultimate reality. That ultimate reality might be something we can't directly perceive, can only infer, and might never, from inside our vantage point, be able to access. This is not a new claim. It has been made in every major intellectual tradition throughout human history. The new thing is the mathematical precision with which it can now be stated, and the physical evidence that is at least consistent with it, and the logical argument that prevents us from dismissing it comfortably. But the existential territory is familiar. You have always been living at one remove from certainty. You have always been an observer inside a system whose foundations are not available to you for direct inspection. You have always had to construct your understanding of reality from the inside out, using only the tools the system provides. That's not a new condition the simulation hypothesis imposes. It's the condition you were already in. The simulation hypothesis just makes it explicit. And making it explicit is, I think, a gift. Not a comfortable one, but a genuine one. Because it frees you from one of the most burdensome assumptions of ordinary life, which is the assumption that reality is exactly what it presents itself as. That the surface is the depth. That what you can see and touch and measure is all there is. That assumption carries a weight you might not notice until it's lifted. The weight of believing that the rules of the visible world are the only rules, that the material is the ultimate, that if something can't be measured, it can't be real. The simulation hypothesis cracks that assumption open, gently, carefully, without replacing it with superstition or fantasy. Just opening a window, showing you the view, letting in a little uncertainty that is strangely a little like air. The strange thing is that when you let that uncertainty in, when you truly sit with the possibility that you might be inside a constructed reality, without trying to immediately resolve it, without reaching for the comfort of a definite answer, the immediate world doesn't become less real, it becomes more vivid. The ordinary things take on a quality they might not have had before, not because they've changed, because you're looking at them differently, because you know, or suspect, or seriously entertain the possibility that this moment, the temperature of the air, the sound in the background, the feeling of being awake and present and alive, is not a given. It might be a gift. It might be extraordinarily, improbably, specifically arranged, and in a universe of that kind, the ordinary is never quite ordinary again. There's a thought experiment I find genuinely useful, and it goes like this. Imagine you're not living inside a simulation, but building one. You're on the outside. You're a programmer, or a scientist, or something we don't have a word for yet. Something post-human, something operating at a level of technological capability that makes our current powers look like a child arranging blocks. You've decided to simulate a universe, a real one, as detailed as you can make it, a universe with billions of years of history, with galaxies and stars and planets, with chemistry and biology, with minds that evolve and cultures that develop and questions that are asked. What do you include? What do you leave out? The first thing you decide almost certainly is the rules, the laws, the fundamental constants. You'd tune them carefully, not randomly. You'd set gravity to a value that allows stars to form and live long enough for planets to develop complex chemistry. You'd calibrate the nuclear forces to allow for carbon chemistry. You'd set the expansion rate of space precisely enough that the universe doesn't either collapse too quickly or expand too fast for anything to form. You'd give your universe the Goldilocks constants it needs to run. Then you'd think about efficiency. You wouldn't render everything everywhere at maximum resolution. You'd use something like the quantum principle of superposition, keeping things undefined until an observer forces a specific value. You'd build in a maximum propagation speed to keep the simulation internally consistent and prevent paradoxes. You'd quantize space and time to give the simulation a finite, manageable resolution, and then you'd populate it. You'd seed the early universe with the right initial conditions. You'd let physics take it from there. The formation of stars, the explosions that scatter heavy elements, the accretion of planets, the slow, blind, elegant process of evolution. You'd wait, and eventually, after billions of years of simulated time, you'd get minds. Minds that look up at the sky. Minds that ask questions. Minds that build instruments to look deeper into the fabric of the reality they're embedded in. Minds that notice the fine-tuning, the quantum weirdness, the mathematical precision, the information bounds. Minds that build eventually the intellectual framework to ask, are we simulated? Now you're on the outside, watching this. You see them asking the question, what do you do? Do you answer? Can you answer? Is there any channel from the inside of the simulation to the outside of it? In most technical frameworks, the answer is no. The simulation runs according to its own physics. There is no message channel built into the architecture. There is no divine intervention function. There's just the code, running, producing whatever it produces. But here's the thought experiment's sharpest edge. You built this simulation, presumably, to study something, to understand something, to preserve something. And the thing that tells you your simulation worked, the thing that demonstrates that you successfully recreated the conditions of the world you were trying to understand, is precisely this. The simulated minds asking the right questions, reaching through the thickness of their constructed reality for the edges of it, suspecting, with surprising accuracy, the nature of what they're inside. If you built an ancestor simulation to understand your past, and the minds in that simulation eventually developed simulation theory and started investigating whether they're simulated, that is a success condition. That is the simulation working exactly as intended. And so, if there is any communication channel from inside to outside, it might not be a signal sent. It might be a signal noticed. We might not be sending a message to our creators. We might be the message. Good science, great science, has always been less about the things that have been confirmed and more about the shape of the things we haven't been able to confirm yet. The landscape of the known is finite and bounded. The landscape of the unknown is what makes it interesting. In the context of the simulation hypothesis, the most honest summary of where we are is this. We know that Bostrom's logical argument is valid. We cannot find a flaw in the trilemma. One of those three options is correct. We know that the physical universe contains features consistent with a computational substrate. The Planck scale, the speed of causality, the quantization of energy, the holographic information bound, the fine-tuned constants. All of these are at least consistent with the designed information theoretic system. We know that information is playing an increasingly central role in the foundational theories of physics. Wheeler's it from bit, Tegmark's mathematical universe, Vopson's infodynamics, Lloyd's quantum computational universe. These are not fringe ideas. They are serious, mainstream adjacent research programs. We know that consciousness remains genuinely unexplained. The hard problem persists. We don't know why there is subjective experience at all, and the answer to that question has direct bearing on whether simulated minds could be genuinely conscious. We know that serious attempts to disprove the simulation hypothesis, including the 2025 UBC Okanagan work using Gödel's incompleteness theorem and Vassar's astrophysical constraints, succeed in ruling out specific types of simulation, but cannot rule out simulation by an entity operating under different physics. We know that the test proposed by Bean, Davudi and Savage, looking for lattice signatures in cosmic ray data, has not yet been conclusively conducted with sufficient precision to produce a result. And we know that the hypothesis remains unfalsifiable in its most general form, which makes it philosophically alive but scientifically unresolved. That's the landscape. It's honest. It's incomplete. It's exactly what you'd expect from a question this large, asked from this particular vantage point, with the tools we currently have. The simulation hypothesis, like all the great questions that sit at the intersection of physics and philosophy, does something interesting when you stop fighting it, when you stop trying to confirm it or dismiss it and simply let it be what it is, an open question with serious logical support and no definitive resolution. It takes on a particular quality, a kind of texture that isn't unpleasant. It sits in the background of thought, the way certain long-form questions do, not nagging, not urgent, but persistent. There when you look for it, changing the colour of things slightly, making the ordinary slightly less ordinary, the familiar slightly less entirely familiar. You've spent nearly 2 hours with this question tonight. You've followed it through the logic and the physics and the philosophy and the counter-arguments and the implications. And if I've done my job, you haven't arrived at a verdict. You've arrived at a more articulate uncertainty. You understand the shape of the question better than you did. You can see where the arguments have weight and where they lose it. You can see what remains unresolved and why. That's not a lesser outcome than having an answer. In many ways, it's a richer one. The question is worth keeping, not obsessing over. Obsession distorts. But keeping, returning to on quiet evenings, on clear nights, in the moments between other thoughts when the mind is loose enough to let something genuinely large move through it. It will keep offering you things, keep opening on new angles, keep finding its way into the corner of your perception and asking gently, but what is this really? And your only obligation to the question is to keep it alive, to not seal it too quickly with a comfortable answer, to let it continue doing what good questions do, which is to make you more attentive, more humble, and more awake to the strangeness of being here at all. Let's let this run quiet for a while, not silent. There's still a long way to go in the gentle drift of this investigation, but quieter, softer. The momentum of argument can carry you through the evidence, but it's the stillness after that lets it settle. Here's something I think is genuinely true. Regardless of whether the simulation hypothesis is correct, the act of seriously engaging with it changes you. It doesn't change you dramatically, the way a crisis changes you, or the way grief restructures your whole inner architecture. It changes you the way a certain kind of sustained reading changes you, slowly, subtly, at the level of basic assumption. Before you spent time with this question, you probably held the physical world as the ultimate reference point. The ground under your feet, the resistance of a wall when you push against it, the weight of a cup in your hand. These felt like the bottom layer, the bedrock, the thing beneath which there is nothing further. After you spend serious time with the simulation hypothesis, that bedrock feeling loosens slightly. The ground under your feet is still there, The wall still resists, the cup is still heavy. But you carry, somewhere in the background of awareness, the small persistent question, what is this actually? And that question is not a destabilizing one, it's a grounding one. Not to the ground you walk on, which might or might not be the deepest ground there is, but to the act of questioning itself, to the practice of not closing too fast, to the intellectual and, in some sense, ethical commitment to staying in contact with the genuine uncertainty of your situation. Because here is what's clear. You exist in conditions of profound epistemic limitation. You're an observer inside a system, using tools provided by that system, trying to understand the nature of the system itself. This is structurally similar to the situation of a mind trying to understand itself using only the mind's own processes. There are principled limits to what can be known from inside, and while that might sound like a reason for despair, it can equally be received as a reason for humility, for patience, for the long view, for building knowledge slowly, carefully, with appropriate uncertainty, knowing that each generation adds something to the picture without finishing it. There's something the physicist Richard Feynman used to do when he wanted to explain what doing physics felt like. He'd talk about the way you could look at a flower and see it two ways simultaneously. The beauty that the poet sees, and the structure that the biologist sees, and the molecular elegance that the chemist sees, and the quantum mechanical substrate that the physicist sees. And none of these ways of seeing diminishes the others. They stack, they compound. The more ways you have of seeing something, the richer it becomes. The flower doesn't lose its beauty by being understood chemically. It gains a dimension. You see the beauty and you see why the beauty is there. The evolutionary pressures that shaped it, the molecular structures that produce the colours, the way light interacts with the specific geometry of the petals, all of it simultaneously. The simulation hypothesis offers something similar. It adds a layer of seeing, not a layer that replaces the direct experience of reality, but one that sits behind it, changing its texture. When you look at the night sky and know that the constants governing those stars were either set by luck or by design or by something we don't yet understand, and that the third option can't be ruled out, the sky doesn't become less beautiful. It becomes differently beautiful, more intentionally beautiful potentially, the kind of beautiful that might have been put there, which, whether it was or wasn't, changes the quality of attention you bring to it, and the mathematics, the equations that describe the sky, the quantum fields, the forces, the space-time geometry. Those look different too once you've considered the possibility that they might be code. Not arbitrary code, elegant code. Code written by someone who understood that the best programs are built on the most compressed, most symmetric, most powerful rules. The equations of physics are those rules. They are compact, they are beautiful, they are unreasonably effective at describing the world. Whether that's because the world is mathematical by nature, or because the code was written by a master programmer, or because something else entirely is going on, the equations are still what they are. And what they are is breathtaking. A short set of symbols, a handful of relationships, a few constants, and from those few things, all of this, everything you've ever seen or touched or known, everything in the observable universe, everything in 13.8 billion years of cosmic history, all of it compressed into equations that fit on a blackboard. That's not evidence, but it's astonishing. It's late wherever you are, or maybe it isn't. Maybe you're somewhere bright and noisy and the world is fully present around you, but this investigation has reached its natural quieter pace, and I want to stay in that pace for a while, because there's something that only reveals itself in the quiet. Not a secret exactly, more like a texture. The world has a texture that only becomes perceptible when you're not rushing through it, when you're just present to it, fully, without agenda. And that texture, the specific quality of experience, the thisness of being here and having sensations and thoughts and feelings, is itself the deepest evidence we have of anything, more immediate than any physical theory, more certain than any philosophical argument. Whatever the ultimate nature of reality is, this is what it produces. This moment, this awareness, this felt sense of being present in a world. That's the output. That's what the universe, or the simulation, or the mathematical structure, or whatever the correct description turns out to be, that's what it generates. And the output is real, not in the sense of being made of some indestructible metaphysical substance. Real in the sense of being what's happening right now. Undeniably, irrevocably, completely. The room around you, real. The sound in the background, real. Your sense of being the one who is present for this, real. That reality, the immediate first person, this is happening reality, is not something the simulation hypothesis reaches into and dissolves. It leaves that intact. It asks about the substrate, the architecture, the level below, but the lived experience itself, the irreducible fact of there being something it's like to be you, that's not up for grabs. That's the one thing the question doesn't touch. We're a civilization that asks whether we're real. This is, on the scale of cosmic time, a very recent development. For almost all of the history of the universe, for the first 12 billion years or so, nothing with the capacity to ask that question existed anywhere we know of. Then there were billions of years during which things existed that had experiences but couldn't reflect on their own nature. And then, very recently, in a blink of geological time, something developed the capacity to wonder about the nature of its own existence, to ask, what am I? What is this? Is it what it appears to be? That capacity, the capacity for philosophical self-reflection, for the kind of inquiry we've been engaged in together, is itself one of the most remarkable things that exists in the observable universe, as far as we know. It might be common. There might be 1 trillion civilizations scattered through the cosmos who are asking the same kinds of questions we're asking. Or it might be extraordinarily rare, a property that emerged once, or a handful of times, in an otherwise unconscious cosmos. We don't know, but we know it exists here, and the fact of its existence here is, whatever your metaphysics, something worth pausing for. Not with self-congratulation, not with pride in the species exactly. The species has also done terrible things with its reflective capacity, and there's no reason to be purely celebratory about it. But with something like appreciation, something like the acknowledgement that this thing that's happening right now, this inquiry, this reaching outward and inward simultaneously, is not to be taken for granted. However it arose, whatever it's made of, it is real and it is rare, and it is happening, and it matters in a way that doesn't require ultimate ontological foundations to ground it. It matters because mattering is what it does. I want to leave you with a question that I think is actually underneath all the others. Not the logical question, which proposition in Bostrom's trilemma is true. Not the physical question, is there a lattice signature in the cosmic ray data? Not the consciousness question, is experience computable? Those are all real questions, and they're worth pursuing, and science will continue to chip away at them over the coming decades and centuries. But underneath them, quieter and more personal is the question, what do you do with not knowing? What do you do when you're an observer inside a system whose foundations are not accessible to you? In a universe that might be base reality, or might be a simulation 7 layers deep, with a consciousness that might be an irreducible metaphysical phenomenon, or might be a particular kind of information processing, asking a question that might never be answerable. You live, you pay attention, you hold the question lightly, and let it keep you humble, and let it keep you curious, and let it prevent you from closing too early around any comfortable certainty. You build knowledge carefully and share it generously. You treat the other observers around you, the other conscious beings in this simulation, or this base reality, or this mathematical structure. with the recognition that they are as embedded in the mystery as you are, that their uncertainty is your uncertainty, that whatever this is, you're inside it together. You wake up tomorrow and make coffee and talk to someone and look at the sky and continue the investigation, knowing that the investigation has no final chapter, that it runs as long as minds run, that it is, in some sense, what minds are for, and that's enough. That's genuinely, quietly, completely enough. We're close to the end of our investigation now. Not the end of the question doesn't have an end, but the end of this particular expedition through it. The territory we've covered is wide. We've walked through logic and physics, through mathematics and philosophy, through consciousness and information, through the arguments for and against, through the personal and the cosmic and the ancient and the new, and we've arrived not at a conclusion, but at a place, a particular clearing in the intellectual landscape where the trees thin out and you can see a long way in several directions without any of them resolving into a clear path. You're in the clearing now. The urgency of the argument has passed. The momentum of evidence has settled. What's left is the ambient hum of the question, the way a piece of music stays with you after the last note has faded, the way a conversation about something real lingers in the room after the people have gone. Let the question stay. Let it hum quietly. Let it be in the background of the rest of the night, the way a certain quality of light is present at dusk, not dominating, not demanding attention, but colouring everything it touches with a specific, unrepeatable quality. You've spent time tonight thinking about the possibility that the universe you're inside might have a layer you can't see, a foundation you can't access, a nature that's different from its surface presentation. And you've found, I hope, that this possibility doesn't drain the surface of its reality. The warmth of the night, or the cool of the air, or whatever is present around you right now, that warmth or coolness is real. The sounds you can hear are real sounds. Your sense of being here in this moment, having spent this time with these ideas, that is real. Completely, unreservedly real. Whatever this is, it includes you. And including you, it includes everything that makes you what you are. Your history, your relationships, your curiosity, your capacity for wonder, your willingness to sit with a question this large for this long. All of that is real in the only sense that matters for it to be real. It is what is actually occurring, right now, in you. And with that recognition resting gently in the background, you can let the rest of the night come. Let the body be heavy and the mind be loose. Let the ideas we've been through settle where they settle. Find the places they fit. Leave the questions they've opened quietly open. You don't have to solve anything tonight. You don't have to arrive anywhere. You're already here. Whatever here is, wherever here is, however deep in the architecture of reality here might be, you are undeniably here. And that's the most solid fact any of this offers. And it's enough. Completely, warmly, finally enough. Near the start of this journey, we mentioned Descartes sitting in his study in 1641, running his thought experiment about the nature of certainty. He was looking for the one thing he couldn't doubt, the bedrock. He found it in the act of thinking itself. I think, therefore I am. The thinking was the proof, not of the world's reality but of his own. And that minimal certainty was enough to build from, enough to go on. We're in a similar place. Not because we've resolved the question he was asking, we haven't, but because we've found the same minimal bedrock. You wonder, therefore you are, whatever you are, however you're constituted, whatever substrate your wondering runs on. You are a wondering thing, and wondering things have been the source of every genuine advance in human understanding of the world. Every scientific theory, every mathematical theorem, every philosophical insight, every artistic breakthrough, all of it issued from the same source, the irreducible capacity to be curious, to ask what is this, to not be satisfied with the surface, to keep looking. You have that. You've had it this whole time, and the simulation hypothesis at its best is not an argument that undermines your confidence in reality. It's an invitation to let your curiosity go deeper than it usually goes, to ask not just what is the universe, but what is real, and what is a construction, and whether those categories are as different as they seem, to let wonder be the instrument, and the question be the territory, and the investigation be the thing itself. Not the means to an end, the thing itself. Sleep well, keep wondering, and be here fully for whatever comes next.